So thank you for the introduction, and thanks for coming to this session. I will start introducing our panelists, and after that we will have a discussion with our panelists regarding the digital twins for the environment, and then at the end I will take questions from the audience here and also from home. Okay, so let's start with Jacqueline Lemoine, who is the Advanced Information System Technology Program Manager within the Earth Science Division of the NASA Science Mission Directorate. Please. Then we have Robert Morris, a senior researcher at NASA Ames Research Center in California. John Blower, the associate director for the Digital Ocean Division at the National Oceanography Center. And then Andy Kingdon, the head of informatics research at the British Geological Survey. So thank you so much for accepting to be part of this panel. So there has been a lot of interest on digital twin lately, especially regarding whether digital twins can make a difference in kind of studying the environment and the climate change. So we are going to discuss this topic, and we want to understand more of what they are and how AI is involved in them, and also challenges and future developments. So I will start with a couple of foundational questions, and maybe I can start with you, Jacqueline. So can you tell us what is a digital twin for the environment?
Okay. So digital twin, and what we call an Earth system digital twin is really an information system that is dynamic and interactive, and that allows to understand, forecast, and hypothesize the complex interaction between multiple Earth systems. So it can be a natural Earth system as well as human or infrastructure systems, and it includes the anthropomorphic impacts and forcings. So at NASA, we define it with three main components. The digital replica, which is the current state of the system, and it's very often what people call digital twin, but the true power of the real digital twin is to add the forecast capabilities and this what-if scenarios capabilities to these digital replicas. So this is what we call the what next, what now, what next, what if. So this, in a nutshell, this is what digital twins are.
Okay. I think a lot of people kind of ask what is the difference between a digital twin and one of the traditional simulators. So
yes.
Maybe you can tell us about that.
Yes, so compared to an Earth system models, I think that this interaction with the user is very important. The fact that the same digital replica can really be used by multiple types of users. The fact also that AI is very present at every level of the digital twin. So it's used for the data fusion, for the forecast, and for the what-if simulations. And also the continuous integration of data is very important, because if you want your digital replica to be a real twin or a fraternal twin, you really need this continuous integration of data that keeps this digital replica up to date.
Okay, great. Actually, this brings me to the next question, which was basically for Bob. Maybe you can start, but the other panelists can add on that. It was about how is AI relevant to digital twins?
Well, I'll quote Peter Bauer, whose webcasts are very interesting to watch, who's part of the Destination Earth program. And he was quoted as saying AI is everywhere, and when it comes to digital twins. And it really is a requirement most people think that if you didn't have AI, you couldn't really develop a digital twin architecture because of some of the requirements that Jacqueline just mentioned about the need for, well, when I first, let me back up, when I first joined NASA, we had a slogan at NASA called cheaper, faster, and better. And in a way, that's what AI offers. AI offers those three things in a way to digital twins, which are very important to digital twins because of the requirements that Jacqueline mentioned about related to infusion of near real-time infusion of data, highly complex models of the interactions between different sub-processes in the environment, and also human, and also interaction with a number of different kinds of user. It's not the traditional, to go back to your previous question, Sarah, the traditional model usually was for earth scientists or data scientists who are interested in understanding the process in the world. But with digital twins, we want to extend the audience or extend the user community for digital twins to include social scientists who are interested in modeling human behavior, and what are called decision makers, people who are interested in, for example, doing agriculture management, water management, renewable resource management, things like that. So we can go into more detail. I won't go into more detail about where AI fits into the picture, but I believe that AI is everywhere or nearly everywhere in the digital twin, in the digital twin architecture.
So do you want to add anything on this?
I guess the only thing I would add is that I think this session is very well titled because it's called Digital Twins for the Environment, not just Digital Twins of the Environment. Mm. So I think we, as well as considering what we would normally jump to, which is simulations and observations of the natural environment, and we build the digital twins for a purpose of helping us to manage that or make decisions around the environment. But one of the things we're really interested in at the National Oceanography Centre is also optimizing our observing systems and using digital twins as a way of understanding how the observations fit into the bigger picture. How do we maximize the investment we make in our observing systems to give us the best scientific value we can from the investments we make? Ocean observations are extremely expensive, however you make them, and we want to be collecting those with a purpose. And I think one of the things, to go back to your original question, that might distinguish a digital twin from just what we would traditionally regard as simulation is the purpose, where we're pointing it towards an activity where we want to make decisions, and that defines how we kind of architect the digital twin itself. But that can be multiple purposes.
Yeah, I think this interdisciplinary aspect of digital twin is also very interesting, and the fact that we can bring together different scientists around it is a very interesting aspect. Okay, so actually I would like to ask you to each one of you if you could illustrate what has been done in relation to digital twins in your institution, and maybe we can start with you, Andy.
We're looking at a whole set of different use cases for how we can understand the environment, and particularly, as a geologist, the impact of the subsurface on the environment. So if you think of a load of people in the UK live very close to the coasts, on cliffs. The east side of the UK is subsiding. The weather and the systems are changing, so they're increasing that rate of subsidence and collapse. And if you live at the top of that cliff, it matters very, very much to you. And if you are a decision maker, be that a central government, local government, environmental regulators, somebody who owns some infrastructure around that coast, maintaining that coast and understanding its vulnerability is really important to you. And so the digital twins have got various importance, but it's the intersection of monitoring and modeling. What are you monitoring? What systems are you using? And what is that teaching you? What isn't that allowing you to model? And in the modeling process, how are you improving your monitoring strategy? So those are really important considerations. But I'm a geologist. I understand rocks. I understand how they behave. I understand how they deform. I don't understand weather systems. I don't understand wave regimes. I don't understand the impact of surface hydrology on a coastal area. So one of the things that's absolutely critical, a piece of work that John and I were involved in, was looking at interoperability of environmental models as part of digital twins. Because the right person to be writing a wave model is an oceanographer. But if you want to study the collapse of a cliff, you need to know the meteorology, you need to know the wave orientation, you need to know the beach processes, you need to know the land surface processes, you need to know the geology. So an absolutely critical part of making meaningful digital twins is being able to take data and models from different scientific disciplines and mesh them together. So that's a lot of work around standards, around semantics, and around interoperability of those to make a model that meaningfully allows you to scenario test what might happen if. And if you live at the top of that cliff and it's your house that might teeter over the edge, then that matters to you very much indeed. So this is a tool to help us solve some really fundamental societal problems.
Great. And John, maybe you can illustrate what is being done at the National Oceanography Center?
Yeah, sure. And just before I do that, I just wanted to strongly support what Andy was saying about the integrating effect of digital twins as a concept. That this is really, I guess we can talk a lot about what the technical details of what a digital twin may or may not involve, but I think what we've seen over the last couple of years is communities are coalescing around this term. They may understand slightly different things about what the term means, but we can open up conversations with groups, stakeholder groups that would have been quite difficult to open conversations with because we have this kind of common conceptual ground. But I think we're at the early stages of kind of exploiting what that actually means. But in terms of what we've actually done so far at NOC, to answer your question directly, we started small. So one of the first projects we had was around developing a twin of what's called a marine protected area. And this is a limited area of the seafloor which is designated as being protected, and there's activities you're not allowed to carry out in that area or are restricted, with the aim of preserving biodiversity. And it is the job of part of the UK government to monitor the biodiversity in this area and to decide what interventions they might make to preserve this. So one of our early efforts to produce a digital twin was to synthesize the data and the models that we have about a particular marine protected area and make that available to decision makers in government departments. But since then, we're looking at many more things. I alluded to digital twins of observing systems. We've been looking at wave overtopping regimes in coastal environments, which impacts upon what Andy was talking about. Also looking very excited about the opportunities for having new modeling opportunities. This is what Bob was talking about. I think the kind of the AI models that would really help us to drive some of these interactive digital twins. So I would say we're still quite at the early stages here, but it's something we have to move forward with as a community, not as individual organizations, I think.
Absolutely, yes. And Jacqueline, maybe you can tell us a bit more about what NASA is doing?
Yes, so right now my program, the Advanced Information System Technology program, has about 16 projects related to digital twins. Some of them are more developing infrastructure for the full information system. Some are focused on AI for surrogate models and emulators. And we have also a few prototypes for wildfire, for hydrology, and for floods, and one for agriculture also. And the one that is probably the most advanced is a coastal zone digital twin, which relates to what you were talking about. And we will probably have a kind of a demonstration prototype by next year. And all of those really fit into a new initiative at NASA, which is called the Earth Science to Action strategy, which is really the idea of being able to use all the earth science products and results for societal benefits, but and to be able to benefit especially climate change type of decisions. Mm-hmm. So all of these prototypes will probably build towards this initiative.
Okay, that sounds good. It seems there is a lot going on in the different institutions. And actually, Bob, I wanted to ask
Could I add something to
Yeah, of course.
I want to put in a plug for good old-fashioned AI, because I think everybody here knows that AI can be broken down into symbolic AI and statistical AI, and most of the real exciting work in AI these days is in statistical AI. But related to digital twins, NASA, for example, is supporting a number of projects in symbolic AI, which is, again, the old-fashioned view where you design knowledge and you use logic to represent reasoning, and you use search to represent answers to tough questions. And when John talked, for example, about managing observation assets, that's pretty much a good application for symbolic AI, planning, scheduling, control. And so we do have a couple projects that feature symbolic AI, and also on the question of smart sensors, autonomous sensors that decide for themselves, whether they plan for themselves or do things like do data processing on board and decide, well, this image is too cloudy, I'm not going to downlink it, so on, those kinds of things. That's, again, usually not a data-driven task. It's usually built on models. So we do have a place for good old-fashioned AI, and at NASA, and there's some really interesting kind of there's a lot of potential for new technologies coming out of there for that. Yeah.
Yeah, no, I agree with you. In fact, I think in a way, not only digital twins give the chance to many different scientists in different disciplines to collaborate, but also scientists in different sub-areas of AI.
Right.
And of course, I think because digital twins are used for decision making, like we were discussing before, I think there is really the need to use AI techniques that are explainable, and we need to be able to really kind of explain to the users how we came to a certain conclusion, and
right.
to show like the chain of the reasoning steps that in a way brought us to conclude something. So yeah, I think we need both data-driven techniques, but also symbolic techniques working together. So yes, my question to you was about whether you think at NASA, or even, I mean, clearly you have done some sort of due diligence about digital twins in other institutions, if you think we have an example, a very accurate digital twin that is already there and has been used to, again, like for decision making and other similar things.
I haven't done a thorough survey of all the efforts, but I would say that we're still at a kind of prototype phase for many reasons. There's a lot of cyber infrastructural changes that need to be made to really realize, I think, the promise of digital twins. More GPUs, more specialized processing units. Different kind of software stack architecture, just pure computing power, and also AI, just to integrate the most recent AI techniques, because the field of AI is changing so fast that we're still testing out kind of it. We have in our program an early stage technology topic area, testing out new ideas. And how old is generative AI? It's not very old. And I think we are still sort of looking at what is the relevance for some of these newest AI methods to digital twins and earth science in general, and digital twins in particular. So we're still at an early stage of infancy, and sort of prototype development. And as Jacqueline mentioned, we do have a number of prototype projects that we're developing, where you do an end-to-end kind of system that demonstrates some of the needs or capabilities that need to be integrated.
Yeah, great. So, Andy, before you were talking about interoperability, so can you tell us what do you think are the main challenges to really, realize this vision of the digital twins for the environment?
Setting questions that you can answer that solve problems and getting all of the information together in a unified form so that you can ingest it and understand the whole system. What we should be looking at is whole system solutions here to try and understand big processes and providing information to decision makers. And last summer I was elected as a local councillor. As well as being a scientist, I'm a witness to, as an opposition councillor, how decisions are made in a practical way. And one thing I've thought about a lot while I've been here the last couple of days is that there's a huge number of really smart people in this room and in this conference hall today. And how do we communicate the information that we're gathering about processes, about trends in data, to people who don't have that same education, to that understanding? We need to find tools to visualize. We need to find tools that show how processes are acting on people and make them take action on the basis of this. Every winter it is a surprise to people that their house is flooded, even though they live in a river valley. And so we need to find tools that communicate complex information to decision makers. Don't build houses there, because that will be under threat, if not now, but because they've done something further up a catchment, it now affects it. So the digital twins are a mechanism to provide complex scientific information to people to make practical decisions. And what we should be looking at is unified architectures to try and synthesize lots of complex different information and provide it to people in quite simple ways that allow them to make decisions. Because presenting people with a scenario-based model with lots of different parameters doesn't help if you're a local councillor or a local council official trying to make a decision about a housing development. But providing them with a map that shows flood here, that might. So all of the things we should think about in this is how we take the complex information we're all working on and provide that to people in a way that they can actually ingest what we're looking at here. One thing that's particularly true about environmental science, which we're all familiar with, is that when you're talking about a digital twin of an engineering system, you're looking at something you understand very precisely to very, very high tolerances. When you're talking about in the environment, it's incredibly complicated and your uncertainties are huge. And when you're dealing with the subsurface, as I do, that's much more true. The percentage of the underground that you actually sampled, so you know exactly what's going to happen, is tiny out of the piece of rock you're looking at for a process. So it's really important that we have tools that can effectively simulate this, that we can test and monitor against conditions, and then use to forecast. Because if we don't go through that monitoring, modeling, overlap stage, then the simulations we make, we can't demonstrate any reliability for them. So we've got to manage that uncertainty. So digital twins are a mechanism for solving a whole bunch of different problems about communicating complex information to stakeholders who, at the end of the day, trying to make really mundane decisions, but we need to give them the tools to do that.
Yeah. Any other comments on the challenges to really implement good functioning digital twins?
I guess in our field, Andy was alluding to it there, we are very observation poor in some aspects. I mean, you can go and buy from a shop a lovely appearing map of the ocean floor, a bathymetric map as we call it, showing all the structure of the ocean floor. There are huge areas of that are actually quite uncertain. And that's really important when if you were to try to simulate ocean circulation in those areas for whatever reason, fisheries or whatever, that's strongly affected by the bathymetry, the topography of the ocean floor, and yet we don't know it in a lot of areas. And sometimes we appear to know it because we have these lovely visualizations, but actually when you go into it, we don't. So one of the things that you quite quickly learn when you try and build a digital twin of part of the environment, you learn where your observations are not adequate quite quickly. And we certainly did that with the case of the marine protected area that I mentioned earlier. So it really kind of redoubles our efforts to think, how should we be collecting more observations to drive these models, to drive our understanding, and how can we reduce the cost of doing so to a manageable level.
Yeah.
Just adding to that, yeah, a lot of what we want digital twins to do consists of predicting extreme events. Mm-hmm. And extreme events, by definition, don't happen very often. Mm-hmm. Yeah. And therefore, the data that you need to train an AI model might not be there. So what do? And this is a problem for any sort of AI model when the data is scarce. That's a critical problem, because it's a feature. You may want to, for example, there's a lot of research in identifying tipping points in nature where a threshold where beyond which in time you can't do anything. You can't reverse the process, and that's obviously very important for us to identify. But how do you train a model to predict tipping points? I certainly don't know. But there is some research in AI currently that is trying to do that. But that's really a fundamental challenge.
Yes, and if I can add something also about uncertainty. Uncertainty quantification is very important, and verification, validation, and uncertainty quantification. So it's important not only at the system level because the digital twin is a system of systems. So the validation of the entire system is important, but also all the different components, because there is uncertainty at the level of the sensors, noisy data that are captured by the sensors. Then there is the uncertainty of the AI, the machine learning that for the forecasting and the simulations. So all of this uncertainty kind of compound on each other, and so we need to be very careful, and it's something that is true for AI also, is that this uncertainty will drive the trust that the users will have in the system, and it's true for AI and machine learning also. So if we can quantify this uncertainty and communicate it well to the users, then they will have more trust in those systems.
Yeah. Yeah, if I can make a different point here, because I'm also an educator, whenever I talk to my students, I teach AI in university, so I always tell them that, in fact, research in digital twin is a very good area to go to do research, because in a way there are so many difficult AI problems that you have to tackle, and so I think by doing research in AI for digital twins, you can really manage to develop critical techniques that then can be ported in other fields, and you can have a very significant impact, not only in the field of AI, but also in the field of environmental science. And so if there are students here, I encourage them to go and try to solve these challenges. Okay, so maybe I just ask a last question, and then we take questions from the audience. So maybe I can start again with Andy, and you can add on that. What should the government's models of digital twin be?
It should be to encourage it to be as interoperable as possible. So we live in a crowded island. There's very few pristine bits of natural environment here. Every bit of environment is populated. Every bit of the environment is used for something, agriculture, forestry, or other purposes. So we need to make sure that when people are building models of natural systems, they can inform decision-making about human systems, and when people are making, looking at the impacts of human activity, that it can inform our models of the natural environment. If we don't make those models talk to each other and communicate and cross-inform, then we're missing an opportunity here. So a lot of that's really straightforward stuff. It's about data formats, it's about proper metadata, verification of data. When you're doing AI-type modeling of any kind of natural phenomena, garbage in, garbage out becomes absolutely paramount. You've got to do some really hard work on cleaning your data and understanding your trend analysis properly. So if we can encourage the government to fund pieces of work that clean off, acquire and clean and manage our data effectively, provide that in a standardized way, then we can start to give them better answers on really important questions about the sustainability of our infrastructure, on the sustainability of our food supply. All these things are fundamental things we need to know about, and we need to have that intersection of different data sets, different understanding, different disciplines, all informing each other, and then we can build really sophisticated systems that really help guide intelligent decision making, which is something I hope we all aspire to.
Yeah, so to expand on that, you wouldn't ask me to build a bridge or a building, because I have no qualifications in the relevant engineering field to do that. But I also don't have any qualifications in digital twin development either, formally. I mean, maybe my affiliation carries with it a little bit of credibility, and maybe I know a thing or two from previous experience, but actually there's no, to build on Jacqueline's point about trusting the observations and about knowing the uncertainties that are inherent in the models, I think we also have to be able to trust the people who are building these things, because the closer we get to informing decisions, I think the more incumbent it is upon us to be doing that in an ethical and transparent and well-intentioned way. How does somebody who we have little previous contact with, the customer, let's say, have that trust in us as providers of information? So I can't help feeling that this is not just digital twins, this is about this area in general, I would say. I can't help feeling that we need to have some professional standards and professional qualifications around this in some way to engender trust in the user community.
I don't think I have anything to add to that. That says it all.
Yes, we were talking about interoperability, and I can see that probably there is going to be an ecosystem. Of course, there is Destination Earth, which is a global, large digital twin, but there are also many local or thematic, smaller digital twins that are going to be developed, and probably there will be some kind of an ecosystem of digital twins that is going to be developed, and that might evolve a little bit, and these will need to interoperate to be able to create larger systems, and I can imagine that maybe these are going to be developed a little bit like the World Wide Web, and if and I am not sure if we will have to develop the standards or if they are going to be developed organically. Mm-hmm. So this is going back to your governance question. I am not sure if it is something that is going to develop organically or if we have to be proactive about it.
Mm-hmm. Great. So I think we can open the floor for questions. Do we have any questions here? Yes, over there, please.
There's another microphone just coming.
I was interested in two kind of slightly opposing things that came up. That Andy, you were saying that we need simple and kind of yes/no kind of visualizations for communication, but also it came up that representing uncertainty and not certainty was also important in some places. What's your different approaches for discovering kind of who wants the crisp version of an answer versus that kind of full representation of uncertainty and difficulty in the modelling?
Anyone?
Well, I'll just mention that when humans express answers that they may not be certain about, they may give a precise answer, but then said, and this is my confidence level. So I think you can have, I think you can have a case where, a prediction, for example, may yield a specific answer, but then accompany it with human explainable qualifiers or confidence rankings. So the main thing is to make, and this is an active area of AI currently, is to make the outputs of the system explainable and interpretable by humans. I don't know if that helps answer your question, but I think you can have both, is what I'm saying.
Any other comment?
It's a real problem. We as scientists, and particularly environmental scientists, deal with uncertainty all the time and try and stress the uncertainty because we don't want to be proven wrong because we've misunderstood the certainty of a system. So that's part of our working life. When we talk to ordinary people, to people making decisions, they don't want to hear that. So there is no neat answer to this, but it's something you have to do. But the ability to test repetitively in a computational environment how a system is going to respond gives you some measure of certainty, and I think that's quite important. But at the end of the day, mostly what somebody wants to hear when you're providing information to a decision maker in government, what they want to hear is a yes/no answer, and we're going to have to find ways to say yes, but more effectively, because there's no neat answers in that space. But you neither want to appear confident about understanding of a phenomenon you don't understand 100%, nor do you want to keep your answer so vague it's not useful. And we've got to find, as a community, we've got to find ways to communicate that. But better trend analysis, better data verification using automated systems, better monitoring, and better visualization of complex problems. All of these things collectively allow you to give more better understood answers to the guy at the sharp end who's got to make a decision about whether something is built there or is not built there or is moved somewhere else, or the real people have to make real decisions about these things. So we have to try and eliminate the uncertainties that we can eliminate, the bad measurements, the poorly understood systems, so that we can then give the best answers we can to people at the sharp end.
Just to briefly add to that, I think what you're talking about is a subcategory of just the user experience in general, of how they use these systems, and the user's experience depends on what you bring as a user as well. Yeah. So whether you find a particular system useful will depend on your use case. I mean, it's almost too obvious to say in a way, but I think everything in that spectrum that we talked about is possible. And it's also where the ethics comes in again as to how much guidance we give, how much do you hide, how much do you reveal. Just as much as the scientific question as what your confidence levels actually are.
So there is an interesting question from a remote participant, Ben, that actually connects to what we are discussing, because he is asking, is there a danger that digital twins will lead us to have too much confidence in our ability to predict the behavior of complex systems? And yeah, I mean, I think this is a valid question. And for example, my research is in autonomous systems, and I've seen this with self-driving cars, right? That although we don't have yet very good systems for self-driving cars, as soon as there are some capabilities that are automated, users tend to trust them, and then of course there are a lot of problems. So I think in a way we should also try to educate people around AI techniques, and how, as we are discussing, in many cases we just have there is a threshold of how much you can trust the systems, and you need to remain alert about the potential cases in which your prediction is not accurate. So I think this is valid for digital twins, but I think this is a real problem. I mean, we should try to consider that.
I think that also we can imagine that eventually for full-blown digital twins, the user interface might not be the same for different types of users. Yes. We cannot ask any user to be able to understand, for example, a climate model. Mm-hmm. So we cannot imagine that a common user will be able to tweak different parameters of a climate models and not necessarily understand what is the outcome is. So this is how we will have to design system where there are different levels of user interface and user access. Yeah. And so this is not easy, but if we can imagine that one digital replica can really respond to the needs of multiple types of users, what we call from farmers to scientists. So these different access will need to be designed.
Yeah.
I was just going to say, I think it's a really interesting question. I like to think of weather forecasting as an example of this, because this is something where we have a very complex system that's boiled down to a small series of numbers for the general consuming public. And no matter what weather app you use, they're all basically the same. They give you sort of very boiled down information as to what they think is going to happen in a certain location. And you might make decisions on it, like whether to bring an umbrella. But we've all built up quite a lot of experience in how to consume weather forecasts. So and for the area where you live. So even though those things are uncertain, you're also, most people are reasonably intelligent consumers of those things. So they might know summer showers are not going to be well predicted in terms of their timing, whereas a winter storm may be better predicted, or continuous periods of sun or something like that. So the user community has a lot of previous experience to deal with the inherent uncertainty in the forecast. I think what we're often talking about here is brand new pieces of information which the user community has no experience with consuming. How does that user community become an intelligent consumer of those systems and learn to interact with a provider to understand what information is really believable out of this? And it's not just about the numbers, it's about all that experience that's built up, I think.
Right. Okay, maybe we can take another question from the audience. Yes?
Yeah, I'm interested about some of the comments you made about bringing together different digital twins from, sort of different academic backgrounds. And we work in defense digital twins, and what we find is they're either super exquisite and work in real time, and therefore it's really difficult to get any sort of sensible machine learning or AI overlay to them, or they're quite simplistic and you can get them to run kind of thousands, if not million times quicker than real time. And you kind of think, well, there's got to be some middle ground, and then is there a case for having standards associated with digital twins that kind of give you, A, the interoperability, and B, the minimum standards you need to actually put a
Comment?
Well, for example, if I take the example of the coastal zone digital twin, I can imagine that there are some global parameters about weather, precipitation that will come from a larger digital twin, such as Destination Earth, for example, and then this. So the smaller thematic digital twin will not have to recreate this information. So the idea is to be able to have like a hierarchy of digital twins where some digital twin will take the more global information from other ones, and then can look at higher spatial or temporal resolution for their particular problems. So this is how I can see different digital twin interoperate. So when I talk about interoperability, is output of one being able to feed as an input for another.
The scale is important here. There's some processes that act at a very big scale and are consistent over a wide area. Some people are trying to monitor processes at a very precise level. I took an email this morning from somebody asking me if I'd speak about digital twins on individual sites and buildings. I'm not going to, because it's an area of precision I have no expertise in. But so we need to be. And one of the things we need to communicate is the scale over which the predictions are valid, and where they beyond the scales at which they are valid, be that smaller or bigger. You're always working within a framework scale, and you need to understand that. But that doesn't mean if you're looking at a particular area, you can't ingest global information into that. But what you can't then do is inform that global information back again. So as John said, there's a lot of things we need to teach people about being an intelligent customer for this. You've got an expertise in dealing with certain types of models already built up. We need to inform our customers about how they use the information and not to overinterpret them.
Okay, so I'm going to ask a question from home. So this is the most voted question. So what are the most important skills or roles required in your team when building a digital twin?
I would say social interaction, maybe, because I think that a digital twin team needs to be multidisciplinary. So being able to develop this common language to talk between multiple disciplines, between biodiversity and climate and weather and hydrology, but also bringing social sciences, even health data in some cases. So I think it's very important to have multidisciplinary teams.
Great.
Yeah, if you look at the structure of or the architecture of a digital twin and the class of users or the different kinds of users that are going to be potentially using the system, it's probably a good idea to have representatives of each. So have a social scientist, maybe have an earth scientist, have a data scientist, have an AI expert, have a decision maker, the person who's going to use the system to predict where the fire is going, the wildfire is going, and which is a big kind of thing for us in California in the past few years. So it's interdisciplinary, and this goes beyond sort of regular earth science modeling projects, earth system modeling projects, where you can probably do with an earth scientist and a data scientist and maybe an AI person, and you're pretty much, that's interdisciplinary enough. But I think with digital twins, it expands the community that you need to include on your team. If you really have the goal of deploying it and deploying it into the real world, I think you need the bigger group.
Yeah, I definitely agree with all of that. I think sometimes the hardest people to find when putting a team together is the people who can take all this and articulate a clear vision for what you're trying to achieve with something that integrates so many different moving parts and potentially benefits different kinds of stakeholders. The sort of person who can synthesize all that information and say, this is what we're aiming for, these are the trade-offs we're prepared to make in order to build this. Because there are so many moving parts in these things, so many different points of view, that you can end up diffusing effort, I think. So having that vision for a project, I think, is really important.
It's a slightly more general point, but this is an AI audience. You can use your AI skills to go and earn a load of money looking at very small changes in banks and making a mint off currency transactions, or you can do something, use those skills to look at environmental systems that matter to populations, that affect people's lives, and you may not earn as much money in that process, but you're doing something worthwhile for human society. So all of you out here there, that if you interact with environmental scientists, if you help us understand environmental systems, the world is a better place for that. And getting AI people who are interested in solving that kind of problem that makes the world a better place. And all power to those of you who've helped in that process.
Great. Maybe you can take a last question from the audience, if we have one. No? Okay, so I take another one from home. Okay, so this participant is asking, all your examples of digital twins are massive scale and complex. Is there a role of small digital twins?
So I think the example I gave of the marine protected area is pretty small. If you can hardly see it on a map, it's really, it's really cool. But I think Jacqueline picked up on this earlier as well, that there's these large efforts, but the decisions are made locally often. So the having ecosystems of digital twins that operate at smaller spatial scales will be where a lot of action is, I think.
Yes, we can imagine that every city might have, in the future, a digital twin. and with all the infrastructure, how to develop, where to develop, but also health information, for example, for air quality, with asthma, for example, related to air quality, health information. So I can imagine that this is very localized, but that it would be extremely useful.
The next twin that I'm going to be involved in building is looking at ground conditions in East London, and it's about, we can see from new monitoring from satellites that there's a lot of ground movement, some of which we understand, some of which you can see. You can see the line of when Crossrail was being built, you can see the line of the tunnel quite clearly from InSAR measurements, but there are processes we don't understand, and what we're trying to do is use the monitoring to understand if we can model it and therefore understand that we get a process out of that, looking at the trends in that, and then use that then as a predictive tool. And that predictive tool is to look at whether what foundations you need behind the houses, underneath the houses that you're going to build to populate for London's growing population. So that's quite small scale. It's a few square kilometres, but that matters. If you're in London and you're trying to find a place to live, that's really critical to you. So yeah. The scale can be what you need it to be to solve your problem. The question is, the issue is asking the right question and getting the right data and the right process understanding to solve your problem.
Yeah, I mean, I guess any complex phenomenon can have a digital twin.
Yeah.
I would just add that the AIST portfolio of projects include projects that I would classify as component technologies for digital twins. It's not a digital twin project, but someone who's developing an emulator of the atmosphere using machine learning methods to generate machine learning models for the atmosphere. That clearly, if you get a fast model, a fast high quality model, that's a component of a digital twin. So you don't have to build a digital twin in order to build component technologies for digital twins.
Great. I think we have to end here. Thank you so much again for being part of this panel, and thank you for your questions and your attention. And